Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Anelen Sindane. The lesson is brought to you by Gauteng Department of Education in collaboration with Saibono Discovery Center. Our lesson for today, we continue from last week where we looked at inverse functions. Last week we looked at the inverse function of a linear function and a quadratic function. Today we will look at the inverse of an exponential function as well as the inverses of restricted linear and quadratic functions. Now the functions will now have restrictions. If you check last week, we did not have much restrictions there. We're just calculating, finding the equation and sketching. Today we'll look at the ones that are having restrictions. Now our objectives for the lesson today, we should be able to understand, sketch and interpret the functions with emphasis on our intercepts with the axis, our axis of symmetry, which is our reflection along the line y is equal to x. We look at the domain and range with restrictions. We'll also look at turning points and end points of our functions. We'll look at the use of laws of exponents and logarithms to solve problems involving the inverse of an exponential function. We are going to sketch and interpret the restricted linear, quadratic, and exponential functions. We can refer to the CAPS document on page 32, and we can also look at our examination guidelines for grade 12 on page 6. Now, our pre-knowledge, we should use our knowledge for sketching graphs. We will use the concept of a function or not, the use of our vertical line test to check if it's a function, as well as our horizontal line test to check if our function is one-on-one. Now, we will also determine the domain and range of the functions mentioned, which is our linear function, our quadratic function, as well as the exponential function. We are going to be solving exponential equations. We'll look at our number systems, looking at sets as well as laws of exponents and logarithms. We should be knowing those. We look at the concept of a decreasing and increasing function with emphasis on the exponential function, as well as our asymptotes. Now, we looked at the first function as well as the second function. Today, our main focus is looking at our exponential function. And remember, we are only going to look at our function which has the form y is equal to b to the power x, where our b is greater than 0 but not equal to 1. We are also going to look at our function where our b is a proper fraction between 0 and 1. Now, we defined a function last week where we said it is a relation in which for every x value, there's in the domain, it's associated with only one y value on our range. And we also looked at a one-to-one function where for every x value in the domain, there is only one y value that is associated to it in our range. And for every y value in the range, there is only one x value that is associated to it on our domain. Now, we also saw that the inverse of a one-to-one function is also a function, after we had explored that the inverse of a parabola per se was not a function because it would fail the vertical line test, and it will also fail the horizontal line test. So we will see that as we move forward, we were able to show that a linear function is a function because for every x value, there's only one y value associated to it, and vice versa. We also looked at our quadratic function. It is a many-to-one function, but we saw that the inverse will not be a function as it fails the vertical line test. You are able to see that for one x value, we have two y values that are associated to that x value. Hence, it's not a function. Now, we discussed as well that the inverse of a many-to-one function is not a function because it will fail the vertical line test. And we saw that a many-to-one function also fails the horizontal line test, as the ruler will intersect the graph at 2 points at the same time, making it not a one-to-one function. We move on. We need to restrict the domain, and we illustrated this by taking half of our quadratic function. We either take this part where we say x is less than or equal to 0, meaning we'll only deal with this part of our graph, then it becomes a one-to-one function, or we may choose to take x is greater than or equal to 0. That is when we are restricting our domain, meaning we will only take the this part of the graph, and it also becomes a one-to-one function, and the inverse of a one-to-one function is also a function. Now, remember, the range of the original function is preserved. So if we are taking this part of the parabola, you are able to see that our range is y is greater than or equal to 0 if we are taking the piece to the left. Also, if we are taking the piece to the right, our y will be greater than or equal to 0 there on our range. The range is always preserved. We move on now. We looked at the process of getting our inverse function. We said if you are given f of x is equal to, you will replace it with y is equal to for our linear function. We noticed that our y is equal to 4x plus 5. We interchange x and y, and we get x is equal to 4y plus 5, and then we make y the subject, and we will get y is equal to x minus 5 all over 4 as our equation of the inverse. We also looked at the quadratic, but we did not look at the exponential function. There is something new that we are going to learn about the exponential function. We have mentioned that the inverse of an exponential function is a logarithmic function. And if we are given y is equal to 1 over 2 to the power x, or y is equal to 2 to the power x, we will interchange x and y, and we will get x is equal to 1 over 2 to the power y, or x is equal to 2 to the power y. Remember, we have to make x and y. We have interchanged x and y, and we have to make y the subject of the formula there. For us to make y the subject, we are going to use a rule that we are going to look at just now. We will look at the inverse of an exponential function, where we are saying the inverse is going to be the logarithm. And this is what is used to solve a non-exponent. And for our purposes of grade 12, we are going to use this mainly when we are solving our exponential equations under sequences and series, especially when we are supposed to find n in our geometric series or sequence, as well as in financial maths, where we are supposed to find, for example, number of payments. We are going to use this concept. So if we are given that x is equal to a to the power y, then we are going to, when we make y the subject, we introduce the logarithm, where whatever is our base in exponential form remains as a base in logarithm. And whatever we have as the product, it's what we are going to put under the log. Our calculators have got this pattern where we are having its log button and another point there. Once you press on that button, it shows on your screen whatever is your base. It's what you are going to put under the first one. Whatever is the value, you are going to put it under the second part of our button there. It will be flickering on our screens, on our calculators, and we use this to solve unknown exponents, and it will always give us an answer. And also, we will be able to see that if we are given that x is equal to the logarithm of base a of y, then we know that our y is equal to a to the power x when we reverse it. So when you are given logs, you are able to write them as exponents. When you are given exponents, you should be able to write them as logarithms. Now, we are able to see that the product is equal to base to the exponent, raised to the exponent, and the reverse, the logarithm to base of the product, will always give us the exponent. For example, if I have 100 is equal to 10 to the power 2, I can write this in logarithmic form. My base is 10, so I can write this as the logarithm to base 10 of my 100 will be equal to 2, which is the exponent there. So we should be able to do this. So if either the exponent is a variable, we are able to get it using the logarithms because we already have the base that we are having there. So we just introduce logs, log, base, whatever the value is our product, then we will get our exponent as the answer there. Now, this can be illustrated using that. If you check 2 to the power 3, our base is 2, our exponent is 3, will give us 8. So 2 exponent 3 will give us 8. And you are able to see that using logarithms, 2 is the base. The logarithm of 8 to base 2 will give us 3, which was our exponent when we are dealing with exponential form. So we should be able to move around in that wheel. We are able to see how to move from exponents to logarithms and how to move from logarithms to exponent, because the examiner can choose to give us any function, hence we should be able to work with whatever we are given. Now, here are some examples. X is equal to 2 to the power y, and I also have 16 is equal to 4 squared. I have to express these in logarithmic form as illustrations. You'll be able to see that x is equal to 2 to the power y becomes y is equal to the logarithm base 2 of x, and 16 is equal to 4 squared. We can write it in logarithmic form. The logarithm of 16 to base 4 is equal to 2. And then we are also able to express, when we are given the logarithmic form, we should be able to write it in exponential form. So the logarithm to base 3 of y is equal to x, we can write that one as y is equal to 3 to the power x, and the logarithm to base 2 of 64 is equal to 6. We can write it as 2 to the power 6 is equal to 64. Now, we move on now and look at the inverse of our exponential function. Now, the inverse of an exponential function is a logarithmic function. So to determine the inverse of an exponential function and logarithmic function, the following conversions, we have already discussed this. So you are able to see that one, it's our logarithmic function. Our exponential function, when our a is greater than 1, we know that this becomes our asymptote, and we know that our function will be an increasing function like that, and in most cases it will always pass through 0 and 1. Now we are able to see that the inverse, the red function, it's our exponential function, and the black function is the logarithmic function. And we are able to see that the two functions will be a reflection of one another about our line y is equal to x, which is our reflection line when we are always dealing with our inverse. So the dotted line is the logarithmic function, and the solid line, it's our exponential function. I can say this is our a to the power of x, and the other one is the logarithm of x to base a. So that is the inverse function. And we know that the y-axis becomes our asymptote for the inverse function. This is going to help us a lot in determining our restrictions whenever we are dealing with our functions. Let's move on now to the decreasing exponential function. We are aware that if our a is a fraction, we know that it becomes a decreasing function, and this is our original function, which is our a to the power x. It's a decreasing function. The inverse is going to be a decreasing function as well. So this is our f inverse, which will be given by the logarithm to base a of x. Our a is a fraction, so we are able to get the inverse function. Please check that if we are looking at the solid line, you are able to see that our x-axis is an asymptote, and our x-axis is y is equal to 0. But if you check the dotted line, you are able to see that our asymptote now, it's now the line x is equal to 0, which explains how we get our inverse. Remember, we said the inverse, it is a reflection of the original function about the line y is equal to x. So the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. So you are able to see that if I'm having a decreasing function like this, our domain is x is an element of real numbers. Remember, it's from negative infinity to positive infinity. But our range for the original function, it's y is greater than 0, because our graph is not defined on the negative side of our y values. Hence, our range will be y is greater than 0 there. But if we look at f inverse, which is the logarithmic function, if you check our domain now, you are able to see that our domain, our graph is not defined on the negative side of our x values. Hence, our domain is now x is greater than 0. And if you look at our range now, our graph continues, it continues. So our range, it's now y, it's an element of real numbers from negative infinity to positive infinity. I hope you are seeing the same discovery we made with our linear function, where we said x and y swap, our x-intercept swap, x-intercept becomes a y-intercept on the inverse function. The domain of the original function becomes the range for the inverse function, and the range of the original function becomes the domain of the inverse function. Let's move along. Remember, the steps we use to sketch inverse functions still apply. We draw a sketch of the original function or the given function, and then we draw our line of reflection, which is our y is equal to x, using dotted lines. And then we take any 2 points on the given function, interchange their x and y values, and then plot the 2 points. We also, now we are able to draw the function for the inverse function, and it becomes a reflection about the line y is equal to x, using the newly plotted points. So the observations that we made using the linear function, we saw that f and f inverse were symmetrical to each other about the line y is equal to x. And we noticed that if a point on f has coordinates a and b, the same point on the inverse function will have b and a swapping positions. The x becomes the y and the y becomes the x value there. We also noticed that the x-intercept of f becomes the y-intercept of f inverse. And we also noticed that the y-intercept of f, it becomes the x-intercept on the f inverse. Now, we notice that the graph of f and f inverse and y equal to x intersect at the same point for a linear function. And we noticed this with the plotting of the graph of y is equal to 2x minus 4. We determined the inverse and we noticed that they were intersecting, and we had points that were swapping positions. Now, you will realize that these will intersect except for the exponential function, which is increasing. When our b is greater than 1, you will find out that the two functions will not intersect, but the reflection line is still y is equal to x, which gives us our axis of symmetry. But the two functions of 1 is equal to f of x is equal to b to the power x, and the one where we have f inverse as equal of x as equal to the logarithm base b of x. If our b is greater than 1, these two functions will not intersect, but the line y is equal to x becomes an axis of symmetry. Now, These are the examples that we have looked at when we're sketching our inverse functions. But remember, we said this one, we are going to look at it with restrictions now, because if we are looking at the inverse function, this one, it is not a function, hence we need to restrict the domain in order for us to have a one-to-one function so that the inverse is a function. Our exponential functions, if our base is a fraction, the two functions will intersect along the line y is equal to x, that is the original function and the inverse function. They will intersect in the first quadrant there. And you will realize that for the increasing exponential function, they will not intersect, but our line y is equal to x is our reflection line there, axis of symmetry. Now, let's look at our example 1. Now, we are given the function f of x is equal to 3 to the power x. The first question requires us to determine the equation of f inverse. So, to determine f inverse, remember what we said. We write this as y is equal to 3 to the power x. Next step, we interchange x and y. We will get x is equal to 3 to the power y. And remember, to make y the subject, we introduce logs. Therefore, our y will be equal to the logarithm base 3 of x. Now, remember I mentioned the issue of the domain and range. So here I can write my domain for the original function. My x is an element of real numbers from negative infinity to positive infinity. My range for this function, my base is greater than 1, which means it's an increasing function. Remember our exponential function, we say f of x is equal to a or b to the power x plus q. And we know that this q is our horizontal asymptote. In this case, our graph will not have an x-intercept, so our y will be greater than 0, because y equals to 0 is our asymptote there. So on our inverse function, we can still write down our domain and range using what we have written there. Remember, whatever is the domain of the original functions becomes the range of the inverse function. So for my inverse function, y is equal to logarithm, let me write it as f inverse x, which is the logarithm to base 3 of x. The domain x must be greater than 0, and my range will be y. It's an element of all real numbers from negative infinity to positive infinity there. 1.2, we are supposed to sketch the graph of f and f inverse on the same set of axes and show the line of symmetry. Now, we are able to do this by saying for our f of x, we know that to get, I can use f of negative 1. It becomes 3 to the power negative 1, and this will give me 1 over 3. And f of 0, this will give me my y-intercept. It will be 3 to the power 0, giving me 1. So my y-intercept will be 0 and 1. And I have another point with coordinates negative 1 and 1 over 3. And then I can try also a positive x value, f of 1, This will give me 3 to the power 1 is equal to 3. So I have another point with coordinates 1 and 3 there. Using these points, I'm now able to sketch a graph. So let's check our 1.2. Yes. So I can say my x my f of x, I had negative 1, 0, 1. So I got f of this, I got 1 over 3, I got 1, and I got 3. So I'm able to sketch my function using that, my Cartesian plane. And remember, we should have our reflection line, y is equal to x. Now, I know that my asymptote here is the x-axis, and along the x-axis y is equal to 0. This is an asymptote. So my graph is an increasing one. I have that point with coordinates 0 and 1, and I've got another point with coordinates 1 and 3, and I have another point this side with coordinates negative 1 and 1 over 3. Remember, we said for our F inverse, I can use the 3 points to sketch my inverse function now. X and y swap position, so it means I have a point with coordinates 1 over 3 and negative 1. I have another point with coordinates 1 and 0, and I have another point with coordinates 3 and 1 that I'm able to sketch here. So here I will have my 1 and 0. This side I must have another point with coordinates 3 and 1, and I must also have another point here with coordinates 1 over 3 and negative 1. Now I am able to sketch my graph using that, and I should remember that this is my f of x and this is my f inverse x, and the equation of this one, it is the logarithm to base 3 of x. That one is 3 to the power x. Now I had my asymptote as y is equal to 0. My new asymptote now, because my graph is not defined that side, is now x is equal to 0. Now I've sketched the original graph and the inverse function on the same set of axes. Axis of symmetry, it's y is equal to x as our line of symmetry. Now we are supposed to write down the domain and range of f inverse. Now f inverse, we say we are able to see that, as I indicated, if you do this on your original function, it's easy to deduce it on your inverse function. I did it on the first slide. You are able to see that for our domain, our graph is not defined on the negative side of our x values, so our domain is x is greater than 0, and our range, you are able to see that our function, it's defined, it is also an increasing function, so it means our y values are from negative infinity to positive infinity. I've chosen to use inequalities, but we can still use our interval notation to represent our domain and range. So using the interval notation, our domain will be x is an element from, you are able to see that it's from 0 to positive infinity. We can't include infinity, hence we use the curly brackets. For our range, our y is an element from negative infinity to positive infinity, using the interval notation there. So this is the same as that, and that one will represent the domain. Now, let's move along. Now, here is example 2. We are given the graph of g of x as a is equal to 1 over 3 to the power x plus 7. And we are given a point that lies on the function. We are supposed to calculate the value of a, and we are also supposed to calculate the coordinates of the y-intercept of g. And 4.3, we are given h of x, which is a new function, as 1 over 3 to the power x. We are supposed to describe the translation from g to h. And we are supposed to determine the equation of the inverse of h in the form y equals, and that question is going to be 9 marks. It's from our June 2022 paper 1 question 4. Now, these are the kind of questions that we are likely to meet in the exam. Let's check. Let's do the first one. The graph of g of x is given by the equation and it passes through a point. How do we find the value of a? Now, I will encourage you to always use your function. Now, we are given E as a point that is on the graph. Therefore, we are going to use that point to help us find the value of A. So, using our function notation, I'm going to write G. I will use the x value there. So G of negative 2, which means where there is x, I'm going to substitute with negative 2. It will be A 1 over 3 to the power negative 2 plus 7. But when my x is negative 2, my y is given as 10. Therefore, I'm able to write this as my A. From our laws of exponents, I know that 1 over 3 can be written as 3 to the power negative 1. And if I have 3 to the power negative 1 to the power negative 2, I will get this as 3 squared. And I know that 3 squared is 9. So this I can write as 9 plus 7. And this will give me 7 and 10. We can 10 minus 7 will give us 3. And this will give us 9a. Therefore, our a is going to be, we divide both sides by 9 and we get this as 1 over 3. Now, if you check, this question was 3 marks. You get a mark for the substitution of negative 2 and 10. We simplify to get 3 is equal to 9a, and we get our a as 1 over 3. That's 3 marks that we can get for free there. The coordinates of the y-intercept of G. Now, remember, how do we get the y-intercept of G? our y-intercept is given when our x is equal to 0. So we have found the value of a as 1 over 3. So I can now write my function as g of x is equal to 1 over 3 times 1 over 3 to the power x plus 7. So to find the y-intercept, I know that my x is equal to 0. So I'm evaluating g of 0, which will give me 1 over 3 times 1 over 3 to the power 0 plus 7. 1 over 3 to the power 0 is 1. So our g of 0 is going to be 1 over 3 plus 7. And this will give g0 as 22 over 3. 7 plus 1 over 3. Remember how we add fractions. If you can't, just use your calculator. 1 over 3 plus 7, it will give you 22 over 3, meaning our y-intercept will be 0 and 22 over 3. So this one, you can get the 2 marks, even if you just write down the answer, our 0 and 22 over 3, because those are the coordinates of our y-intercept. So for substituting 0 and then getting 22 over 3 will give us the y-intercept. We move along and we are able to see this. Now, describe the translation from G to H. You are moving from our G of X is given as 1 over 3 to the power x plus 7. Now, I can write g of x as bases are the same. Using laws of exponents, I can write this as 1 over 3 to the power x plus 1 plus 7. You are moving from here to get h of x, which is 1 over 3 to the power x only. Now, if you look at this one, so to get h of x in terms of g, this is g. I want to get power x here. It means for this one, I must subtract. So it becomes g of x minus 1. For me to get 0 there, I'll get plus 7 minus 7. So which means this will be g of x minus 1. And here instead of having, we'll have minus 7. So that if I have 7 minus 7, I'll get the 0 there. So this is the rule that will make us get our h of x. Now, we are describing this using our words. So we can use the equation or you can use the words. If you check, it's g of x minus 1. So it means our g of x is translated one unit to the right, 1 unit to the right, and you are able to see that for us to get 0, it's 7 minus 7. It will be 7 units downwards. So you get a mark for 1 unit to the right for the direction and 7 units downwards. So our translation can either be up and down, left, right. So we will get our 2 marks there. We are supposed to determine the inverse of h in the form y equals. Now, remember, we said our h of x is that one, so it's y is equal to 1 over 3 to the power x. We interchange x and y, we will get 1 over 3 to the power y. Therefore, our inverse function becomes y is equal to the logarithm. Our base is 1 over 3 of x. So it's the logarithm of x to base 1 over 3. Or using our laws of exponents, I can write this as y is equal to 3 to the power negative x. I interchange x and y. I will have x is equal to 3 to the power negative y. And I will have this as y is equal to negative logarithm to base 3 of x. This is also how we can write our inverse function. But it's safer to leave it there. But I'm just saying you must know all the forms so that if you are given one, you are able to see how you can work around it. Now, I will give you 6 minutes to do activity 1. 6 minutes. I want us to attempt activity 1. Where the graph of g of x is that one, and we are supposed to work through it. I will ask you to use 6 minutes to answer those questions. Right, welcome back. Let us now look at the questions. We are given the graph of g of x is equal to a to the power x, which is drawn in the sketch on the side. The point S has coordinates 2 and 9, lies on G. We are given that point S. T is the y-intercept of G. So the coordinates of D, how do we get our y-intercept? We let so G of 0 is equal to a to the power 0. And any base raised to exponent 0, we know that g of 0 is going to be 1. And we know that the coordinates of t will be 0 and 1. 2 marks, substitution, answer. Calculate the value of a. To get the value of a, remember we are using our function notation g. In place of x, we are using the coordinates of point S. When our x is 2, it means this will be a to the power 2. And we know that g of 2 is equal to 9, and we'll have a squared. And 9, we know that is 3 squared is equal to a squared. Therefore, our exponents are the same. We can equate the bases. Our a is equal to 3. Again, substitution and answer, we get our 2 marks. We move on now. We move on to the next part where we are supposed to find the graph of h is reflected by reflecting g in the y-axis. Write down the equation of h. By reflection about the y-axis, this becomes our reflection line, which means the mirror image of g comes this side, and we will have our function looking like that. So this point S, we are now having S prime, which is the image, and it will have coordinates -2 and 9 like that. The y value remains the same, but the x values are now negative. Whatever we had as negative x values, they are now positive after the reflection. So in other words, we are saying the equation of h of x is given by g of -x, and we know that g of -x becomes our base. We got it as 3 to the power -x, and we can write this as using our laws of exponents. Remember, we said 3 to the power -x. We can write it as 3 to the power -1 to the power x, which will give us 1/3 to the power x. So that's 2 marks. We move on now. Write down the values of x for which 0 is between the logarithm of 3 of x to base 3, which is less than 1. Now, remember, we know that we are having a point here with coordinates 1 and 3, and we have this point T with coordinates 0 and 1. If we are to quickly sketch our in y is equal to x, we know that this will give us our inverse function, and our inverse function is also an increasing function. The coordinates here will be 1 and 0, and we are able to see that somewhere here we are also having coordinates 3 and 1 on the inverse function. This is our g inverse. This is our g of x. Now, let's get the solution there. How do we write down the values of x? for which 0 is less than the logarithm of x to base 3 less than 1. This is a point on our inverse function. You are able to see that when our y is 0, we are able to get that one. And let's get the values of x. How do we do it? We know that we can write this as 3 to the power 0 is less than 3 to the power of our logarithm to base 3 of x, which is less than 3 to the power 1. And we know that this will give us x. 3 to the power 0 is 1, and 3 to the power 1 is 3. So our x values, you are able to see that this is between 1 and our 3 there. This is how we are interpreting the solution to that question. And you are able to see that g of x is an increasing function. Therefore, we will get our solution using that. So it's between our x is equal to 1 and our x is equal to 3 there. That is when our logarithmic function is between 0 and 1. We are looking at our y values there. We move on now. Remember, I mentioned the concept of restrictions of our domain. Once we restrict our domain, it means our range also is going to be restricted. Let's check. If I have f of x is equal to x squared, where x is greater than or equal to 0, it means this is a restriction because I'm only looking at half of the parabola. And the given function would look something like that. When my x is 0, when my x is 1, and when my x is 2, I'm able to get those 1, 2, 3 points. And I'm only dealing with half of the parabola where I'm saying my x is greater than or equal to 0. I'm also able to get my range as y is greater than or equal to 0 because my y values, the minimum is 0. It means my y values are all positive there. Now, so when we are dealing with a restricted function, it is important to always write down the domain and range of the original function, as I have done. My x is greater than or equal to 0. My y is also greater than or equal to 0, so that it is easier for you to deduce the domain and range of the inverse function using that particular function. Now, let's look at that example. We are given that f of x is equal to x squared, x greater than or equal to 0. We are supposed to write down the range of f, the original function. So you are able to see that if our x is greater than or equal to 0, our y is also greater than or equal to 0. So I will answer A. The range of f y is greater than or equal to 0. I've answered that one. The equation of f inverse. So the equation of f inverse, this will be my y is equal to x squared. I interchange x and y. This will give me my x is equal to y squared. I have to make y the subject, so my y is equal to plus or minus the square root of x. But now, because I'm only dealing with a restricted domain and range, it follows that my y will be equal to the I will only take the positive square root of x because my x is greater than or equal to 0. Whatever was my y here becomes my domain here. And my range also is given by y is greater than or equal to 0 there. And using that, I will use the points that I plotted in the example. I will draw my Cartesian plane, and you will find out that we said we had points with coordinates 0 and 0 there. When I substitute 0 into the original function, I also have coordinates 1 and 1. I also have 2 and 4. I know that I have my equation of axis of symmetry, y is equal to x, my reflection line. And I will interchange x and y. I will have a point. I will have another point here with coordinates 4 and 2. This is my f. This is my f inverse. I've done the sketch of the two functions on the same set of axes and show the line of symmetry. Now, so this is what we will get. We are only looking at the positive square root, and you are able to see that our x is greater than 0 or equal to 0, and our y is also greater than or equal to 0. That is the sketch of our original function as well as its inverse function. Now, we are also going to look at the restricted linear function, and I will give that one to you as an activity. We have done example 3. Let us now look at our activity 2. I will give you 8 minutes to do that activity 2 in 8 minutes. Right, welcome back. I hope you had a good time doing this question. Now, you are able to see that now our domain is restricted, which means our graph is terminating somewhere, which means our range will also be restricted. Now, the first question says, determine the coordinates of Q. If you are looking at that graph, our endpoints, you are able to see that it ends, our x value, it's 4 there. So here it means we are having 4 and h of 4 as the coordinates of that point. Here it means our coordinates are h are -2 and h of -2. Now, moving from there, those are our endpoints. If you look at Q, Q is our x-intercept. How do we get the x-intercept of a linear function? We know that we are going to let our h of x to be 0, and we are solving the equation there. And this will give us our 0 is equal to 2x minus 3, and we will get our x as 3 over 2. So the coordinates of Q will be 3 over 2 and 0. We move on to the next one. Write down the domain of H inverse. Remember, for us to be able to determine the domain of H inverse, we must get the range of the original function. So our original function, we have to get h of -2. This will give us 2 -2 minus 3, and this will give us -7, and h of 4, which will give us 2 times 4 minus 3, and 2 times 4 will give us 8 minus 3. This will give us 5. So it means the coordinates of the endpoints here, it's 4 and 5, and the coordinates here are -2 and -7, which means for our range for this particular function, we are having -7 is less than or equal to y less than or equal to 5. So whatever, this is the range for our original function. Remember, whatever is the range here, on the inverse function, it becomes the domain. This domain here becomes the range. So it means our domain for H inverse will be -7 is less than or equal to x less than or equal to 5. You are able to see that one there, and we get our domain as such. So we are going to get 3 marks there for calculating the y values on our endpoints, and then using them to see that whatever is the domain is the range on the original function becomes the domain on the inverse function as illustrated. So I just want to bring to your attention the importance of these endpoints. You know that if we are using less than, we are not including the value at the endpoint. So for example, if the range was -2 less than x, the domain, is less than or less than 4 like that. It means the endpoints here will not be dotted, but they will be just left open like that. The endpoints will not be shaded. Remember, we did this when we're doing inequalities. If it's less than, we just indicate the endpoint, but we do not shade it. But if it's less than or equal to, we are including the endpoint, it's shaded. So please take note of that, because we have to be careful of our signs that are used on the question. If it's a less than, it means we'll maintain a less than sign. If it's a greater than, we maintain it. So we have to be careful on how this is indicated, because it will also determine our range, which will eventually determine the domain for our inverse function. We move on to the next question. We are supposed to sketch the graph of the inverse function, clearly indicating the y-intercept and the end points. Now, so our end points, we noticed that on the original function, this is 4 and 5, -2 and -7, like that. These will swap positions, meaning on our inverse function, we are going to have our domain. It's now from -7. So the coordinates of this point now are -7 and -2. The coordinates of this point are now 5 and 4. And remember, the coordinates of Q are now the y-intercept, which is 0 and 3/2, like that. Hence, we will have our graph and we show the endpoints like that. It's still an increasing function, but it terminates when our x is -7 and when our x is +5, like that. So we have clearly indicated our endpoints. And remember, this is what I was trying to illustrate. If this was a less than sign, it means this point will not be shaded now on the inverse function. But because we're using less than or equal to, it is shaded. We are including that point. For which values of x will h of x be equal to h inverse x? Remember, for this one, either we are going to use the equation of the inverse, or we are going to use, remember, we have our axis of symmetry, which is given by y is equal to x. Our graphs are going to intersect somewhere if they have to intersect. So for which values of x will h of x be equal to h inverse x? Remember, we said these will intersect at y is equal to x, first equation. Second equation, 2x minus 3. We have y is equal to 2x minus 3. Second equation, we solve these simultaneously. We'll get x is equal to 2x minus 3. And this will give us our x is equal to 3. We substitute when x is 3, our y will also be equal to 3. So it means we want for which values of x will h of x be equal to h inverse x. So for this particular one, we just needed the x values, and we will get our answer as x is equal to 3. We do not need the y value there. So we just want the x value. But once you get the x value, you are able to get the y value. So sometimes they ask for the coordinates, sometimes they just ask for the x value. So we are able to do the calculations accordingly there. So for knowing, generating the two equations, equating them, then getting our x, we will get our 3 marks there. Now, let us do activity 3. I will give you 4 minutes to do activity 3. Welcome back. Interesting activity to help us remember what we need to do. The graph of f of x is equal to 2 to the power x is sketched alongside. There is our graph of f of x. Give the coordinates of a. So if you check, a is our y-intercept of f. So to get the y-intercept, so we know that our x is 0 there. We can evaluate f of 0, which is 2 to the power 0, which will give us 1. So it means the coordinates of a will be 0 and 1. So for answer only there, you can get marks because you know that the y-intercept, it's 1 mark there. Write down the equation of f inverse in the form. So we know that y, this is 3.1, 3.2, y is equal to 2 to the power x. We interchange x and y, and we will get x is equal to 2 to the power y, and we know that y will be equal to the logarithm of x to base 2. Interchanging x and y, and for the answer, you get your 2 marks there. For which values of x will f inverse be less than or equal to 0? Remember, here we said the coordinates are 0 and 1, and we said this is an increasing exponential function. That would be our axis of symmetry, and the inverse would look something like that. It will pass through 0. Sorry, it will pass through 1 and 0 there. So the y-intercept becomes the x-intercept there. So our graph is like that. So it means, where is the inverse function below? It is between 0 and 1, because remember, our y-axis becomes an asymptote. Our graph is not defined there, hence our graph, our x values will be between 0 and 1. So the answer for 3.3, we can write it as 0 less than x less than or equal to 1. Or remember, if you check, our graph is less than 1. Can you see our y values there? It's between 0 and 1. So it means this on the inverse function becomes our x values. It's still between 0 and 1. Remember, along this line, this is an asymptote. Our y cannot be equal to 0, but it has to be greater than 0. Hence, we will get our answer there. Write down the equation of the asymptote of. So f of x, this is 3.4. So for the end points and the correct inequality signs, you get your 2 marks there. We want to find f of x minus 1 is equal to, it means 2 to the power x minus 1. Now, we know that still the value of our q here is 0, which means we only have our horizontal asymptote, meaning our y is equal to 0. This is our horizontal asymptote. This becomes the equation of our asymptote, because 2 to the power x minus 1 does not affect our horizontal asymptote. We move on to the next one. Activity 4. I will give you 4 minutes to do activity 4. Welcome back. I hope you had a good time doing this question. Now it says, sketched is the graph of G, the inverse of a restricted parabola. This is the equation of the inverse. Remember, we are saying our y is equal to x squared. Ax squared is the equation of the original function. So to do this one, we are going to say we interchange x and y. Our x is equal to a y squared, because this is the inverse. Now, in other words, we have to get the value of a first before we can move on. If you check on our inverse function, our x is going to be 8 and our y is going to be 2 squared. In other words, this means this will give our equation as 8 is equal to 4a, and our a is going to be 2. So, moving forward, we have to determine the equation in the form y equals. So, using that, our equation will be given by y is equal to, we want the equation of the inverse function, the original equation. So we are now saying moving forward from there, we are saying our x is equal to, our a is 2y squared. In other words, our y squared is equal to x over 2. Our y is equal to plus or minus the square root of x over 2, like that. Now, but which arm of the parabola are we looking at? If you look at the inverse function, our x is greater than 0 and our y is also greater than 0, meaning we are also looking at the y is equal to plus, we are looking at the positive square root of x over 2, where our x is greater than or equal to 0 and our y is greater than or equal to 0, like that. Now we are supposed to write down the equation of the inverse function in the form y equals. So remember, we are able to do that one. We already have our inverse function, which means the inverse is going to be the original function that we start with. Because this is the inverse, it means the inverse of this one will be like that, where we have our axis of symmetry going that way. So the inverse of that will be given by y is equal to 2x squared, where our x is greater than or equal to 0 and our y is also greater than or equal to 0 as our restriction. We move on now to 4.3. We are supposed to give the coordinates of the turning point of f of x is equal to g inverse x plus 3 minus 1. What will be the turning point of this function? In other words, we want to find out the coordinates of the turning point, because our g inverse x is equal to 2. In this case, we are replacing x plus 3 squared and minus 1. We know on our normal functions, we know that the turning point of this one, it's shifted. If it's a plus, it's shifted 3 units to the left, and -1, it means it's 1 unit down. So in other words, this will give us the turning point with coordinates -3 and -1. We get our 2 marks there. Because of time, we are not able to complete activity 5, but it's taken from the June 2018 question 4. You can go and do that one later on, and we are able to show you the solutions there of 4.1, 4.2. There are the solutions without using the calculator. We are going to use our laws of exponents, and our P will be equal to 2 for 4.2. 4.3, the equation of the inverse in the form. We know how to get the inverse, and we should get the inverse. That one, it's in the form of a log, so our inverse will be in exponential form. So we know how to do that. The range for the inverse, you know that whatever is the domain for the original function becomes the range for the inverse function. And then the points of reflection there, we should go and look at our transformations and how we do the reflections and so on, so that we see how we get our coordinates. Activity 6 is also another restricted parabola. We are able to answer the question there. It's extracted from March 2016 paper 1, question number 6. Now the solution, we are able to see the solution there. In summary, we now know that the inverse of a one-to-one function is also a function. The inverse of an exponential function is a logarithmic function from what we have looked at. We also know the process of getting the equation of an inverse function. We swap x and y, and we make y the subject again. The domain and range of the as function must be written down to help find the domain and range of the inverse function. Now, we are also going to be dealing with restricted functions. We know that for a restricted function, the domain of the original function becomes the range of the restricted function. And we should be able to determine those whenever we are working with our functions. Thank you very much. Enjoy your afternoon.